So this should also be pretty much 100% review from what we talked about back in Circuits 1. I just want to make sure that is aware of the process and all of that kind of good stuff. One thing that I will say is that obviously for the in-class portion of your exam related to this material, I can't give you any circuits that would require you to use nodal or mesh analysis because you're expected to be able to solve the circuit with your calculator. That being said, on the take-home portion of your exam, obviously I can ask you literally anything I want because you have your computer and MathCAD and all of that kind of good stuff available. So I would be more than happy to show you guys how to use MathCAD to set up systems of equations using complex numbers and all of that kind of good stuff. If you happen to need that review or if you've never had it shown to you. But if you don't tell me to do it, I'll just assume that you know how to do it and we'll go on and do other things. Okay. So I've just brought a random textbook out of my collection of circuit analysis textbooks. And ultimately, all I want to do is just look at a couple of problems here and see if we can sort through how things work. So let's see. This looks like a reasonable example. So I'm going to start with this particular circuit where I have a time domain voltage source, and I'll give it a label here in just a moment. So right now I'm just going to call it Vs of t in series with a 125 millihenry inductance. Then I have here a 120 ohm resistance. Here is a 140 millihenry inductance in series with a 5 microfarad capacitance in series with an 80 ohm resistance. And I'm going to close this guy off right here. And let's say that we were interested in determining the following quantities. So I'm going to call this current right here Ix of t, and I'm going to call this voltage right here Vy of t. So our ultimate goal here is to get a time domain signal for the current flowing through that 120 ohm resistor and a time domain voltage for the voltage drop across that 5 microfarad capacitor. And let's say that Vs of t has a value of 18 cosine 800t plus 115 degrees volts. Okay? So for a circuit like this, our first step should always be to convert this circuit from its time domain representation into its frequency domain representation, meaning that we're going to replace all of our currents and voltages with their phasor equivalent. And then we're going to replace all of our resistors, capacitors, inductors with their impedances. Okay. So in the frequency domain, what is our 18 cosine 800t plus 115 degrees volts going to look like as a phasor? 18 angle 115, absolutely right. So we don't need to do anything particularly special here because we had a cosine representation already. So we can just take the magnitude, take the phase angle, throw the rest away. If this were a sine function instead of a cosine function, we would have had to have remembered to subtract 90 degrees from that phase angle to get it into our correct phasor form. All right, now I'm going to just continue drawing things here. We'll talk about the values of stuff in a moment. So I'm also going to go ahead and convert those unknown quantities that I'm solving for into phasors as well, right? So the current flowing through this resistor, now I'm going to represent it as a phasor current IX. And similarly, the voltage drop across this capacitor, I'm going to represent as a phasor voltage Vy. Now, we learned back in Circuits 1 and also reviewed last Monday that the impedance of a resistor is simply the resistor value itself, right? So that means that this 120 ohm resistor is going to continue to look like a 120 ohm resistor, and this 80 ohm resistor is going to continue to look like an 80 ohm resistor. We also learned that the impedance of an inductor is given by J omega L. So we have two different inductors here, a 125 millihenry inductor and a 140 millihenry inductor. So let's do both of those in turn. So here's J. What is omega for this system? 800 radians per second, absolutely right. So for those of you who may not remember, omega is literally always the thing that's being multiplied by time inside of our sinusoidal signal, okay? So that's where we're going to get omega 100% of the time if it's not explicitly told omega is something, okay? So 800 radians per second. And then we're going to have an inductance. Let's start with 125 millihenries. And so I think this is going to come out to be somewhere in the ballpark of J80. Oh, just 100? Okay, yeah. I should have been able to do that math better. 800 times 1/8 seems like it should be 100, but I'll just double check. Yep. So this is going to be J100 ohms. So I'm going to replace this inductor with a J100 ohm impedance. And for my second inductor, I'm going to have that same angular frequency of 800 radians per second times 140 millihenries. And that comes to be J112 ohms. Lastly, we have our capacitor, where the impedance of a capacitor is given by 1 over J omega C. So that's going to look like negative J divided by 800 radians per second times our 5 microfarads. And I wind up getting negative J 250 ohms. So now our circuit has been completely switched from the time domain into the frequency domain, which means instead of using calculus and trig, we can simply use algebra and DC circuit analysis techniques. So with that in mind, how might we go about solving for either of these quantities that we're interested in, our phasor current Ix or our phasor voltage Vy? So the current flowing through the J100 ohm resistor is not going to simply be 18 angle 115 over J100 because the total voltage drop of 18 angle 115 doesn't occur over just the J100. We could take your idea and slightly modify it and do a source transformation, which would allow us to then do current division to find that quantity Ix. We could also use current division to find the current flowing through that rightmost branch and then use Ohm's law to find Vy. So that's definitely one way that we could approach it. Another way, when I was looking at this thing, I thought about doing voltage division to find the voltage drop across the 120 ohm resistor in parallel with that series combination of elements on the right-hand side. That would allow me to do Ohm's law to get Ix, and then a second application of voltage division to get the Vy that we're looking for. We could also do effectively a modified nodal analysis. So essentially, if I treat all three of those elements on the right as a single impedance, I could figure out what the voltage drop across the 120 ohm resistor is just by doing KCL. And then I could find Ix by using Ohm's law, and then Vy using voltage division. And then, of course, we could also do nodal analysis, or we could also do full-on mesh analysis. So literally, the sky is the limit here. We just talked about 5 or 6 different ways to do this. We would realistically just do whatever we're most comfortable with. So with that in mind, what circuit analysis techniques are you guys least comfortable with? And we can try to use that in order to solve this system so that you get some more familiarity with it. So how do you guys feel about current division, voltage division, source transformations, things like that?
I'd probably say source transformation.
So source transformation is what you're least familiar with. Okay, so let's use a source transformation here then. So just to revisit the concept of source transformations, whenever I have a practical voltage source, which is nothing more than an independent voltage, or actually, let me rephrase that, a ideal voltage source in series with an impedance in this case, I can transform it into a current source in parallel with that exact same impedance. And the rules for this transformation are literally just governed by Ohm's law. So the current that I'm going to get is simply that source voltage divided by that impedance. So taking this one step further, using a source transformation, we are going to now have a current source. So if the positive polarity terminal of our voltage source was on top, the head of the arrow for our current source should be pointed up. Okay. And this is now going to be in parallel with that J100 ohm impedance. And the value of this current source is simply going to be 18 angle 115 divided by J100. So 18 over 100 is going to be 0.18, if my memory serves me correctly. Yeah. So this is essentially going to look like 180 angle, let's see, so 115 minus 90 is going to be 25 degrees milliamps now. Okay. And I'll just make a note right here that this is literally just 18 angle 115 degrees volts divided by J100 ohms. Double checking my math here. Yep. Continuing to redraw my circuit. Now I have my 120 ohm resistor over here. Here's J 112 ohms of inductance. Minus J 250 ohms for my capacitance. And then 80 ohms down here for this resistance. Our quantity Ix is still just going to be the current flowing through that 120 ohm resistor. And the voltage Vy is still just going to be the voltage drop across the minus J 250 ohm capacitance. One thing that I do want to warn you about using source transformations. So if you're using a source transformation and the voltage across any part of that practical voltage source is something that you're interested in, or if you're doing a source transformation and the current flowing through one of those branches of that practical source is something that you're interested in, doing a transformation there can be very tricky because when you transform things, you're changing the physical position of that element within that circuit, and that may not translate easily to understand where that current or where that voltage should be once that transformation occurs. So generally speaking, I wouldn't perform a source transformation on this guy if, say, for instance, this was a voltage that I was interested in, because changing its position completely changes where I'm actually looking for things at. So just wanted to make you aware of that. There are some constraints on what we can do. So now that we have this particular system, I personally would probably use current division to find the current IX. So applying current division, we would say that IX is going to be equal to our known current, which is 180 angle 25 degrees milliamps. And then in my numerator, I'm going to put the reciprocal of the branch that the total impedance of the branch that I'm interested in, which in this case is going to be 120 ohms. And then in the denominator, I'm going to put the reciprocal of all of the three branches that are in parallel. So that'll be 1 over J 100 ohms plus 1 over 120 ohms plus 1 over, and I'm just going to do this as 80 ohms plus J 112 minus 250 ohms there. So that last term is all three of those. So that's the J112 ohm impedance from the inductor, the minus J250 ohm impedance from the capacitor, and that 80 ohms impedance from the resistor, all put together and treated like a single impedance for that branch. Okay. So I'm going to take a moment here and throw this into my calculator. So 1 over 120, 1 over 100 I plus 1 over 120 plus 1 over 80 plus 112 minus 250 I. So if I put this into my calculator correctly, I get 121.397 with an angle of 46.738 degrees milliamps. Okay. So before we move on from here, does anybody have any questions, comments, or concerns about how I wrote my my current division relationship or anything like that? Kobe, how may I help you?
So the current division will be just the IX times the current we already have times everything in parallel, right?
So applying current division, it's the known current, which in this case, so I know that this 180 angle 25 degrees milliamps is going to divide in some way, shape, or form between those three parallel paths, okay? So it's my known current multiplied by, and now I have a ratio of impedances, okay? In the numerator, I should put the reciprocal of the impedance of the path that I am interested in. So I'm trying to find the current through the 120 ohm resistor, so I put 1 over 120 ohms in my numerator. If I was trying to find the current flowing through this branch over here, I would put that total impedance in my numerator, okay? And the denominator is simply the sum of the reciprocals of all of the parallel paths that the current can split between, right? So we have three different parallel paths connected to this current source, one having an impedance of J100 ohms, one having an impedance of 120 ohms, and another one having an impedance of, looks like 80 minus J 138 ohms, if my mental math is correct. But I chose to write everything out so that you could see where that was coming from. So if I had 5 parallel paths, I'd have 5 terms in my denominator. Okay. And we're always doing the reciprocals when we're doing current division. Okay. Any other questions about how we set this up or anything like that? All right. So we've got IX taken care of. So just for the sake of argument, so I've shown you a source transformation. I've shown you current division. So I'm going to use Ohm's law to find this voltage Vx, which is just going to be the voltage drop across the 120 ohm resistor. And then I'm going to use that to do voltage division to find Vy, just to make sure you all are familiar with voltage division and all that kind of stuff. Okay. So our voltage Vx is just going to be our 120 ohm resistance times our phasor current Ix. So that's 120 ohms times this 121.397 angle 46.738 degrees milliamps. And I got a voltage of 14.568 with an angle of 46.739 or 738, excuse me, degrees volts. So conceptual question here. Does it make sense that the phase angle of that voltage Vx and the phase angle of that current Ix are the same? Yes, because it's a resistor, right? If it were a pure inductance, we would see that the current would lag the voltage by 90 degrees. If it were a pure capacitance, we would see that the current would lead the voltage by 90 degrees or be 90 degrees more positive. Okay. So we can now do voltage division to solve for that voltage Vy. So Vy would be simply equal to Vx multiplied by, once again, a ratio of impedances, where I put the impedance that I'm interested in finding the voltage drop over in the numerator. So that's going to be minus J 250 ohms. And then I'll put the total series impedance in my denominator. So in this case, that is going to be 80 ohms plus J, and then I'm going to have that 112 minus 250 again, like so. I wound up getting 22.8315. So I'm going to call that 832 with an angle of 16.637 degrees volts. Kyle, how may I help you? So technically, yes, we could have done voltage division from the jump, right? So I would once again call this voltage right here Vx, and I would have to solve for that voltage Vx, probably using voltage division, and then I would have done a second application of voltage division to find that Vy once we figured out what Vx is. For that first application of voltage division, for what it's worth, I'll just do a quick kind of sketch of what that would look like, right? So Vx, solving for it directly, would have been that 18 angle 115 degrees volts. And then in my numerator, I would have had to have that total impedance. So that's the 120 ohms in parallel with 80 plus J 112 minus 250 over 120 plus 80 plus J 112 minus 250 all over 120, excuse me, J 100, excuse me, plus, and I'm just going to put numerator here because I'm running out of space, but it's literally exactly what I put in the numerator. So we're just treating all of this like it's an equivalent impedance, and we're just finding the voltage drop across that equivalent impedance. Okay, so assuming I've typed things into my calculator correctly, um, are we done? So fantastic. So we were trying to solve for Ix as a function of time and Vy as a function of time. So we are not quite done. We are incredibly close. Our last step is simply to convert back from the frequency domain to the time domain for those two signals of interest, right? So Ix as a function of time, I'm simply going to take my magnitude of 121.397, and now I'm just going to have cosine of omega t, which was, omega was 800, and then I'm just going to bring that phase angle in for my phasor of 46.738 degrees milliamps, and I'll follow a similar process for Vy of t, right? So my magnitude was 22.832 with a cosine of 800t plus 16.637 degrees volts. What's up? Let me answer call first. So if I ask you for a time domain signal, I expect you to convert it back into the time domain. If I ask you to give me a phasor voltage or current, then leave it in the frequency domain. So it entirely depends on what is asked of you.
You always want it in the cosine form, or can we leave it as a negative sign?
So if we are given a phasor, then we already have it in the cosine form. The only thing that we're adding is actually the cosine omega t part, because this magnitude is for the cosine form, and this phase angle is also for the cosine form. So whenever you're working in the frequency domain, we're using cosine as our fundamental basis. That's how we generated our phasors to begin with. So when we transform back, we're always going to have cosine functions. We would have to actually do more work to convert it into a sine function or something like that.
So if our phase angle was like negative, would you leave it as a minus 90 degrees?
I personally would, yes. So I am expecting the result to always be magnitude cosine omega t plus phase angle. It's not a huge stretch to convert between sine and cosine because it's just a 90 degrees phase difference and all of that kind of stuff. But I've never seen anybody actually bother to do that. So, yeah, I don't think I would count it wrong if you did it. I would just question why you're doing more work. So any other questions or anything about this guy? All right. I don't know. Let's find another problem then. Let me find something that looks more difficult. No, that one can just be easily solved. This one looks potentially gross. All right, so let's say that we have the following circuit. Where once again, I'm going to have some voltage source Vs of t, and I'll tell you what that is in a moment. Here I have a 20 millihenry inductance, a 20 ohm resistance. I'm going to put a dependent source here. So this is going to be 25 times, let's call it Ix of t, where this is the quantity Ix that we're interested in. Here's a 10 microfarad capacitance. Here's a 30 ohm resistance. Here is a 10 millihenry inductance across which I'm going to have some voltage Vy of t. And I'm going to close things out here. Okay. And let's say that Vs of t is 48 cosine 2500 t plus 45 degrees volts. And ultimately, we are interested in solving for Ix of t or Vy of t. Now, I think technically, I was about to say, I think technically this might be doable with a single application of KCL, but we would actually have to get fairly creative for that. So I think for this one, it's probably actually going to be easiest to analyze this using nodal or mesh analysis. So which one of those two analysis techniques do you guys feel the least comfortable with? You feel least comfortable with mesh. Surprising. Let's do it with both. Okay. So let's take one crack at it with mesh so that we can see how that works. We'll take one crack at it with nodal. But regardless, our first step is going to be to convert from the time domain into the frequency domain. So what is my phasor source voltage going to look like? Yep, 48 angle 45 degrees. What should my 20 millihenry inductance look like? So 20 millihenries is 0.02, isn't it? Yeah. So I got J50 when I did that. My 20 ohm resistor is still going to look like a 20 ohm resistor. So this is going to be 25 times my phasor current Ix now. What's my 10 microfarad capacitor going to look like? I got minus J40. So 1 over 10 times 10 to the sixth, or excuse me, minus 6 times 2,500, right? Yeah, I got 40 the second time I typed it in as well. So is it minus J25 or is it minus J40? Okay. All right, so minus J40 ohms. What's the 10 millihenry inductor going to look like? And by the way, you shouldn't need a calculator for this. Exact half of the other one, right? Since the inductance of the 20 millihenry inductor had an impedance of J50 ohms, so 10 millihenry of inductance should have half as much, so that'll be just J25 ohms. Where this voltage is now going to be our phasor voltage, Vy. Okay, so let me make a copy of this thing for when we do our nodal analysis here in a couple of minutes, okay? So mesh analysis seems like a perfectly reasonable thing to do here, as does nodal analysis for what it's worth. So starting with mesh analysis, I would probably say this is going to be my mesh current I1. This will be my mesh current I2. And this will be my mesh current I3. So I don't, excuse me, the first thing I would do is define my controlling variables for my dependent sources in terms of my mesh currents. So my first equation is simply going to be Ix is equal to something. So I think somebody said negative I2, so that's going to be part of it. I1 minus I2, right? So it's the mesh current in the same direction minus the mesh current in the opposite direction. So I1 minus I2. I don't have any current sources, so I won't have any current source relationships. So, and I also won't have any super meshes, so I can just go straight into my KVL from here, right? So I would do KVL at mesh one. So I would write this as negative 48 with an angle of 45 degrees volts plus J50 ohms times I1 plus 20 ohms times I1 minus I2 is equal to 0. Then I would have my KVL at mesh 2 relationship. So that's going to look like 20 ohms times I2 minus I1 minus 25 IX. Was it 25 original? Okay, it was. Plus negative J40 ohms times I2 minus I3 is equal to 0. And then lastly, I would have my KVL equation at mesh 3, excuse me. And that's going to look like minus J 40 ohms times I3 minus I2 plus 30 ohms times I3 plus J 25 ohms times I3 is equal to 0. And I now have a four equation, four unknown system that I would use a computer to solve. So you guys want to jump into MathCAD now and solve this one, or do you want to do the nodal analysis and then use MathCAD for both things or whatever? MathCAD now. Okay. So anytime we're solving a system of equations, we're going to wind up using what's called a solve block. So I'm just going to go ahead and put a solve block in. For what it is worth, solve blocks are only available in the paid version of MathCAD, which you all should have access to as Louisiana Tech students. So if you see that this solve block thing right here is grayed out, sometimes the license server has a hiccup and you might need to reconnect to that license server so that you can access our license for all of that kind of good stuff. The information for that should be available on our Canvas page in the introduction section where it says MathCAD 8.0 Prime download. So if you don't have MathCAD installed, that's also where you'll go to download the software and all of that kind of stuff. So I'm going to have four different variables in this system. I'm going to have my three mesh currents. So I'm going to start with, sorry, I must have caps lock on, I1, and I'm going to use the shift colon equal sign. And I usually tend to put the just the number one as my guess values. So because I'm dealing with complex numbers, I don't think this is necessary. It's just the habit I've gotten into. I'm going to do 1 angle 0. The angle operator is gotten by pressing Control Shift P. Okay. Or if you don't know the keyboard shortcuts and you literally click this operators button and go down here under engineering, that's where you can find the angle operator, but Control Shift P is way faster if you know it. Okay. Then I'll put 0. If we go back here in this operator section and we mouse over the degree symbol, there isn't a keyboard shortcut given to us, but it will take the letters D, E, G and interpret that as a degree symbol. So that's how I do it. And then I also make a point to explicitly multiply by the units in this case. So that's, open parentheses, 1 angle 0 degrees, close parentheses, times amps. The reason why I explicitly multiply is because MathCAD can be very finicky and sometimes it will treat things like functions when you don't want it to. And if you multiply on the outside of the parentheses, it will never treat it like a function. So I'm going to just follow through here and do the same exact thing for mesh currents. Control Shift P, there we go. 2 and 3, as well as our current IX.
So we do this with any variable we have.
Exactly right. So you do it with all the variables that you have to be very explicit. So I had 3 mesh currents and an IX. I have 4 equations, so I'm going to need to have 4 variables up here. Okay. So I have essentially set some initial value for the computer to start its iterative process of solving for these quantities by those guess values. For what it's worth, you can set your guess value to 0 the overwhelming majority of the time, but sometimes that breaks, which is why I just choose to use 1 for everything. Okay. The guess values don't particularly matter too much until you have polynomial equations, and then they become incredibly important because whatever solution to that polynomial is closest to your guess value is the one that the computer is going to return. If you need it to give it all of the different solutions, you have to use the symbolic solve function and all of that kind of good stuff, which we'll be doing a whole heck of a lot of in circuits 3 when we have really gross things and we're using Laplace transforms and stuff like that. All right, so let's see here. Now I'm going to put in my constraint equations. So these are just the 4 equations that we developed. So the first equation that we had was for Ix, and in this constraint section, I use the control equals equal sign. So that's a boldface equal sign. And what that equal sign means is make sure that whatever is on the left of this equal sign is exactly equal to whatever is on the right. So that's how it's forces those things to be equal to each other and then iteratively solves this system. So I believe this was just I1 minus I2. That is not a 2. There we go. Then I have my KVL at mesh 1 equation, which would have been negative 48 angle 45 degrees volts plus an impedance of, I think it was J100 ohms. So I'm going to do 100J, and then I'm going to multiply by an ohm symbol. For what it's worth, the ohm symbol is just Shift W to give you a capital W, and then Control G to convert that capital W into Greek. Sorry, I'm distracted by some dude carrying a ladder behind you. He moved to the right, so he might show up out of that window in a moment. But anyway, thank you, you're right. So 50J, and the multiplication here is critically important, okay? So let me show you what I mean. Right now, this J is in non-italics, right? So it's treating that J as if it were the imaginary operator, the square root of -1. If I get rid of, so if I just did J and then omega, without that multiplication sign, it's italicizing that J, which means it thinks it's part of some variable J omega, which is very much what we do not want. So that was just 50J multiplied by capital omega. And then that should be times I1. And then I'll have plus 20 ohms. Must have hit something weird. Multiplied by I1 minus I2. And oops, I should have done control equals 0. Now I have my mesh 2 equation to write. So that's going to be 20 ohms times I2 minus I1. And then I'm going to have minus 25. And I'm just going to leave it as 25 right now, but I know it's going to give me an error in a moment. Times IX. And then I think that was minus 40J ohms times I2 minus I3. Now I have my KVL equation for mesh 3, which should be minus 40J ohms times I3 minus I2 plus 30 ohms times I3 plus 25J ohms. I don't know why it keeps doing that. Times also I3. That is not what I wanted. Control equals to 0. And I've got my 4 equations. Now I'm going to use my solver. I have gotten in the habit of always trying to save my variables into a matrix in case I need to use them outside of the solve block. So I'm going to put all 4 variables in here. It is important. I see students make this mistake very regularly. However many variables you have up here in your guess area, you need to have the exact same number that you're solving for. If you don't solve for all of them, MathCAD freaks out and gives you weird results. So I1, I2, that is not a 2, I3, and IX. Shift colon equals find, and then those exact same quantities in the same order. And I'm expecting it to tell me units don't match. These units are not compatible. So the reason that it's telling me that these units are not compatible is because here I have 20 ohms times I2 minus I1. So 20 ohms times the current gives me a voltage. This is 25 times the current. So it's interpreting that as a current because I did not put the units on that scaling factor of 25. So because that is a voltage controlled current source, the units on that should be volts per amps, or we could just as easily call it ohms, but I typically do volts per amps. So now this should totally work, okay? Um, right now it's giving me my answers in rectangular form with I as the imaginary operator, which I don't particularly care for. So if I go over here to the math formatting tab and click down here, I have options for rectangular with I as the imaginary operator, rectangular with J as the imaginary operator, polar form where my angle is expressed in pi radians, polar form where my angle is expressed in radians, and finally polar form where my angle is expressed in degrees, which is what we're used to. So one other thing real quick, I just want to show you guys something. So this is why I harp so much on units, right? So I'm going to delete that thing right there, and I'm going to put just 20 ohms times that thing. And it freaks the hell out. What it's telling me when I mouse over this is that this value must be a function. So what it is doing is it is saying, hey, this is 20 multiplied by some function omega that depends on I1 and I2. That's why explicitly multiplying is so important. And I probably use more parentheses than I need to just to cover my ass, but I'm so used to getting these errors that I just intuitively do things to make sure that they don't happen. So I'm gonna just put parentheses around that and then multiply and it's fixed.
So does MathCAD have an output terminal to specify where we're getting an error or like better describing error?
I genuinely do not know. I feel like if you went into the documentation and all of that kind of stuff, it would probably tell you. No, that's not documentation. Maybe it's in the resources. Um, references, tutorials, help, all of that kind of stuff. I feel like there's probably a better explanation there. I have literally never looked at it. I just, whenever it's telling me the units are not compatible, 99% of the time it's because I forgot to put units on either a current controlled voltage source or a voltage controlled current source. And if it's telling me that it's expecting a function, it's because it's treating something like a function. So I go and figure out where I forgot to accidentally multiply. And that was just lots of trial and error on my part. Those are the two um, errors that I most frequently get and I most frequently see students get. So we found our phasor current IX that we were interested in. How would we, if we go back to our circuit diagram here, how would we find that voltage VY that we're interested in? So I3 times that impedance of J 25 ohms. Yep, absolutely. So outside of the solve block, I can say that Vy will be colon equals to, or it's a shift colon, 25J ohms multiplied by I3, and I get that result. For what it's worth, I believe if you just have your cursor out in the field like this, and you go to the math formatting tab, it will do everything in whatever math complex form that you're interested in for the rest of the page instead of having to do it individually. I found that out earlier this year, so I had been doing it for 7 years, doing every individual thing in specific ways. So I just thought I'd let you know because it's not as intuitively obvious as you would think it was. Just for the hell of it, what I'm going to do now is I'm going to show you what happens if we don't store all of that information in a matrix. Yep.
So, put, 4x1 matrices, and we like type it all out, and then we actually try to solve, what were you saying we have to do to get it in terms of like the correct variable, I believe, or in the correct, like format?
Okay, so there's a math formatting tab up here at the top. So you click on it. And then in this little part of the, I don't know, ribbon or whatever the hell it is, um, this drop down menu, that's so when you mouse over it, it says complex values. And it provides you a drop down menu that you get to choose how you want your complex numbers represented. All right. So if I didn't have this matrix here and I just delete this stuff, it's freaking out now because all of my variables essentially only live inside my solve block unless I explicitly tell it to save them somewhere. So that's what that matrix was doing at the beginning, right? So this matrix right here, if I put it in the right damn spot, essentially stores the result of this find operation and allows me to use those values outside of my solve block for any further calculations that I might have to do. So I am of the opinion that it is always good practice to store your values in that matrix so that you can use them later for things. All right, we've got 15 minutes left, so I'm going to write down these results real quick, and then we're going to run through a nodal analysis. And then I might do the MathCAD sheet for the nodal analysis and then upload both of these sheets for you onto Canvas just so that you have access to them. So 0.509 angle negative 44.614. 0.509. Oh man, I can't remember a damn thing. Negative 44.614. And so Ix of t is 0.509 cosine 2500 t minus 44.614 degrees amps. And then we also found Vy to be 14.669. With an angle of 5.581 degrees. Volts. And from this, Vy of t is 14.669 cosine 2500 t plus 5.581 degrees volts. Sorry, I was running out of space down there. All right, nodal analysis. Well, that doesn't help me at all. Oh, that is it freaking out. Oh, Control Z, Control Z, Control Z. Get rid of that dumb thing. Go up here. Retake a picture of this. Put it back to where I want it. Get rid of my mesh currents, and now we'll take a stab at node. All right, so where would you guys like me to put my ground or reference node? Bottom. Okay, that seems like a pretty reasonable place. So I'm going to say that I have 1, 2, 3, 4 unknown nodal voltages, like so. So running through my nodal analysis process, I typically start with my controlling variable relationships first. So how am I going to express that current Ix in terms of my nodal voltages? V2 over 20. Thank you very much, Kaylee. I have 2 voltage sources, so I'm going to have 2 voltage relationship equations. So I'll start with that 48 angle 45 degrees volt source. So how does that relate to my nodal voltages? Just V1, absolutely right. And then I have my 25Ix dependent voltage source. How does that relate to my nodal voltages?
V3 minus V2.
Exactly right. Thank you for that. So I do have a supernode, right? So I have, or well, actually all of my voltage sources are supernodes, but I have a supernode that doesn't contain ground. So I'm going to have to write a KCL at this supernode equation. So that's going to be this, that's a shitty looking arrow. This current flowing out plus this current flowing out plus this current flowing out plus this current flowing out. So let me just write this down. KCL at supernode 2, 3. And that's going to look like V2 minus V1 over J50. Plus V2 over 20 ohms. Yep. Plus V3 over negative J40 ohms. And then plus V3 minus V4 over 30 ohms. I'm going to set that equal to 0. And then my last equation should be KCL at node 4. So that's going to look like V4 minus V3 over 30. Plus V4 over, let's see, what was that guy? J25. Is equal to 0. And now I have a 5 equation, 5 unknown system. I don't honestly know if 5 minutes is long enough to throw all of that into MathCAD. I sincerely doubt that it is. So like I said, I'll do that on my time here in the next couple of minutes and then just post this MathCAD sheet on Canvas so that you guys have access to it if you need it for anything. All right. So I hope you guys have a happy and safe Easter break. I will see you in a week.